And so the value function for a policy tells us how much total reward we expect to get going into the future. So we're going to look at the expectation over the future of the reward at time t, plus the reward at the next time step, plus the reward at the next time step. And we can also have this discounting going into the future. This is something that says we care more about immediate rewards than later rewards. So we'll understand this in more detail next lecture, but just to give you some intuition, this is a really central idea that we care about basically how much total reward we can get from some state onwards if we're going to follow this particular behavior. If I'm in my helicopter and I know that I'm going to execute some particular trajectory, how much reward will that trajectory get me? That's what we're trying to say here. And if we can compare these things, then we've got the basis to make good decisions, because we know which of those, should we choose the trajectory that's going to get us 73 points of reward in total, or should I choose the trajectory that's going to get me 65 points of reward? Well, it's obvious when you say it like that. So the value function is a really helpful quantity for optimizing behavior. Okay, so I'm just going to do one more video just to make this idea a bit more So this is the value function in Atari. So what we're looking at here on the top right, we look at the top right, is exactly this quantity V that we were just talking about, saying how much reward the agent thinks it's going to get going into the future. And the one down the bottom is saying how much reward it thinks it's going to get for each different action. Just back up a little bit. And what you'll notice is that there's this sort of oscillating behavior where each time the bat is getting, each time it hits the ball, it was going to get more reward. Let me just back up a second, we can look at that. Here. So each time the ball is getting closer to hitting something, it knows it's just about to get this reward. There's no uncertainty left. And so it gets this big spikes in the reward according to this. And each time the ball's coming back down, the predicted future reward is going down, and so you get this sort of oscillating behavior. And it's only when the agent's actually close that it matters which way it goes. It has to make a decision when the ball's coming down of whether to go right or left. And until it gets right there, it doesn't really matter which one it chooses. Now for Space Invaders, what we see here, let me just back up again, is that what we see is that there's basically, we'll see a big spike, which is when the mothership starts coming along the top, it realizes that mothership might mean a big spike in possible reward it's about to get. Like if it actually shoots that mothership, it should expect to get a very large positive reward. And so when that appears in its state, when it starts to see this thing, its prediction of future reward should go up. And so that's what we see, is that now this mothership comes up, the value function starts to climb, it misses the opportunity to get it, and the value function goes back down again. Now we see another example. The value function is kind of flat, it's getting all of these things as it's shooting. Here comes the mothership. This time it shoots it, and the value function still goes back down, because we're always just talking about the future reward. The value function is how much reward we expect to get in the future. So the fact that we've just got that reward, so now we've received that reward, but we still predict that we're going to get less reward from now on, because the mothership's already come, we've shot it, it's probably not going to come again for a while. Okay, so we've got like this agent's internal measure of how much reward, how much score it's going to get going into the future from here. And this thing is like its oscilloscope of how well it's doing at any given moment in time. So it can be used to make decisions. Yeah.
So this reward is predicted in, let's say, 1 second, right? It's not predicting the end of the game, or just
Yeah, the reward has a time scale to it, and the time scale, if we just go back to the time scale, so the question was, is there a time scale to how far ahead we look in, is there a horizon to how far ahead we look into the future for these scores? And the answer is that the horizon is given by this discount factor. So at every step we discount the reward a little bit more and a little bit more and a little bit more going into the future until essentially we don't care about things very far into the future. So for that particular example it was about 0.99, the discounting, which means that we're essentially looking, say 100 steps into the future. Yeah?
Is there some sort of a risk-reward trade-off between the value functions? So for example, you care about value functions which have a lower expectation but are more stable in terms of actions you do.
Okay, so the question is there some kind of like risk trade-off that you can make where you can, for example, can you balance variance of these reward predictions? The answer is that ultimately what we care about, we've defined a formalism in which what we care about is just the amount of reward we get, and if you care about just expected reward, then risk is already factored in. That you will figure out the behavior which correctly balances risk automatically if you optimize for this. However, there are people who specifically try to do, for example, trading, who take account of risk, and there's risk-sensitive markup decision processes which do try to explicitly account for this. So if you really want to bring in risk, you can, but I think the right way to think of this is that risk is already accounted for. That it will automatically, the behavior that maximizes value is the one that correctly trades off the agent's risks so as to get the maximum amount of reward going into the future. And that just automatically emerges from the formalism. Okay, so so remember we talked about these different quantities. So we've had the policy and the value function. So now let's talk about models. So a model is basically, it's not the environment itself, but sometimes it's useful to imagine what the environment might do, to try and learn the behavior of the environment, and then use that model of the environment to help make a plan and to help figure out what to do next. So specifically, the way we normally do this is to have two parts to our model, transition model and a reward model, where the transition model is basically predicting what the next state will be, predicting the dynamics of the environment. So if this was the helicopter, this is the thing that says that if the helicopter's facing this way in this position with this angle, and the wind is coming in this direction, then it's likely to move to this position and this angle, and so forth. That's the dynamics of the environment. And we can try and model those dynamics. We can try and learn what will happen to that helicopter at the next step and figure that out. And we can also learn to predict how much reward we'll get. So we can learn that if the helicopter's in this situation, that it's not crashing and that we'll get one reward for staying alive or whatever it is. And so formally we break this up into a state transition model that just tells us the probability of being in the next state given the previous state in action, and a reward model that tells us the expected reward given the current state in action. Okay, so it's optional to do this, and actually a lot of the course will focus on model-free methods that don't use a model at all. So this isn't a requirement. It's not necessary to explicitly build a model of the environment, but it is something you can do. So let's try and make these concrete in a very simple example, which is a maze. So this maze example is like a canonical RL problem. These little grid worlds, we use them for sort of didactic purposes. And so the idea is we're going to start here and try and get to this goal here, and there's going to be a -1 per time step reward, just like the question earlier. The goal here is essentially to solve this maze as quickly as possible, and that's reflected by this -1 per time step, and the problem will finish when the agent reaches the goal. So solving this, the optimal solution will be just to whiz around it as quickly as possible. And the actions are just like four connected, like it can go north, east, south, west, and the state is basically the agent's location in this grid. Okay? So an example of a policy would be represented like this. That these arrows are an example policy that sort of represents what the agent would choose to do if it was in any one of these states. So this is an example of a deterministic policy function that says, if I'm in this state, go left. If I'm in this state, go up. If I'm in this state, go right. It's a mapping from states to actions. Once you have this mapping, you can just kind of read it out and behave. Like the agent can just read out its behavior and just move all the way to the goal, and we'll get there. So that's what we mean by a policy. We mean like these arrows here. The value function, remember we're going through these three key concepts. So the value function looks something like this. This is the value function for each of these states, where we know that if we're just about to reach the goal, we're only one step away from the goal here, so this must have a value of -1. Here we're 2 steps away from the goal, so this has a value of -2. If we go all the way back to here, we have a value of -16. We can have worse values. If we're stuck over here and we've gone the wrong way, we might have a value of -24. Now we have these values. It's very easy to build an optimal policy because, for example, when we get here, we can just look up what's the value of going north compared to the value of going south, and it's very clear that the value of going north is greater than the value of going south, and so this is useful gives us a basis for optimal behavior. And finally, a model. So let's say the agent has seen one trajectory through this maze, kind of moved around like this, and then it reached the goal, and now it tries to build a model of how this environment works. So you can think of this as it's trying to kind of build its own map of the environment. It's trying to figure out what will happen in the environment. And the model in this case would look something like this, and these -1s represent the fact that it's seen that you get -1 per step, and this map represents what it's understood of the dynamics of the environment so far. It understands that as you move around, these are the transitions where you can move from state to state. It's not reality, it's just the agent's model of reality. Okay. So when we categorize RL agents, we can basically build a taxonomy now where we can taxonomize all of reinforcement learning according to these three quantities. And the way that I taxonomize RL is basically by which of these key components our agent contains. And so we say that when we build a reinforcement learning agent, we say that it's a value-based algorithm if it contains a value function. And if it just contains a value function, the policy is kind of implicit. It just has to read out, look at the value function and pick the best action. Just like when we were here, we didn't need an explicit representation of policy because we could just look at our value function and say, hey, the value function here is higher than the value function here, so always just pick actions greedily with respect to your value function. And so that basically gives us a way to behave and means that a value-based algorithm can look like this, just a value function and no policy, or an implicit policy.
I'm just curious, why in the previous slide we mark all the points with -1?
So the question was, why were the -1s on the previous slide from? So the -1s were the agent's model of how much immediate reward it gets at every step. So it's basically saying it learns, so the setup of this problem was -1 per time step, no matter what happens. And so now the agent's map says that each step it takes, no matter where it moves, it's going to get -1. So this isn't the value, this isn't a long-term prediction of reward, this is a one-step prediction of reward, saying every single step it's going to, you can go from here to here and get -1, here to here you can get -1.
Okay, but we didn't define the direction, right? If we would go from this second to...
Yeah, sorry, it's just in this down here. So the numbers here represent the immediate reward from each state, and it's the same number for all A, just as an easy way to define this. In general, you would want to have a different number for each action. Sometimes there are different formalisms for reward, and sometimes you can have action-dependent reward, sometimes action-independent. It's a good question, but kind of detail. Okay, so to categorize the agents, they can be value-based, or they can be policy-based. So to build a policy-based agent means that now, instead of representing inside this agent the value function, how well it's going to do from each of these states, instead we explicitly represent the policy, and we work with the policy. So those arrows that we had here, so a policy-based agent would maintain some kind of data structure equivalent to these arrows, and it would work directly in that space. It would basically look at how well it does and adjust these arrows so as to get the most possible reward, without ever explicitly storing the value function. So that's what a policy-based agent means. A policy-based agent is one that stores the policy. A value-based agent is one that stores the value function. And we can also have what's called an actor critic, which basically combines them both together and tries to get the best of both worlds. So an actor critic, which we'll see later in the course, is an agent that stores both the policy and directly represents these arrows, and also stores how much reward it's getting from each state. Yeah?
Well, what do you do in the way of exploration? Like, say you...
I'm going to come back to it. The question was, what about exploration? I've got a section on that coming. Okay, so to finish the taxonomy, now we can either have a model or not have a model. So first of all, one of the major distinctions in reinforcement learning is between model-free and model-based reinforcement learning, perhaps the fundamental distinction in RL. So model-free means that we do not try to explicitly understand the environment. We don't try to build the dynamics of how the helicopter moves. Instead, we go directly to the policy or the value function. So we just see experience and figure out a policy of how to behave so as to get the most reward, without going through this indirect step of figuring out how the environment works. So that's model-free reinforcement learning. And a lot of the course will be about understanding how that can be possible. You know, how do you even do this without building a representation of the environment first? Alternatively, we can do model-based reinforcement learning, where we first of all, our first step is to build up a model of how the environment works. We first build our dynamics model of the helicopter, and then we plan with it. We do look ahead. We say, you know, what would happen if we looked ahead with this model and figured out the optimal way to behave. So we have something like this Venn diagram now, where we can either have a value function or not, we can have a policy or not, we can have a model or not. Now, ultimately, you have to behave, the agent has to select actions, and to select actions, really it needs to have a policy to pick it, or a value function that implicitly defines a policy. So the majority of algorithms look like that. Okay, so this is our taxonomy of RL agents and how to understand if you pick up a random paper from reinforcement learning, it will fit in somewhere in this diagram. Okay. So briefly, for the last 5 or 10 minutes, I just want to talk about some problems within reinforcement learning. So we've talked about the reinforcement learning problem overall, but there are some key sub-problems that we're not going to talk about how to solve these, but just to name them and make you aware of their existence and to start thinking about them is my goal at this stage. Okay. So let's start with learning and planning. I think this is maybe the most important conceptual distinction to understand. There's actually two different problems in sequential decision making. So if we go back to this science of what does it mean to make optimal decisions, there's two very different problems we might care about. First of all, there's what we call the reinforcement learning problem, where the environment is unknown. Like the agent isn't told how the environment works. You literally just drop your robot into the factory floor and tell it to get the most reward. Or you turn on your power station and you tell it to go and figure out how much reward it gets. You don't tell it how the wind blows or how the factory operates. It just figures stuff out for itself. And the way it does that is by interacting with the environment, and through interactions with the environment, figuring out a better policy that's going to maximize reward and get the most possible future reward. So this is the reinforcement learning problem. Doesn't know about the environment, interacts with the environment, essentially through trial and error learning, figures out the best way to behave within that environment and maximize its reward. Okay. There's a second problem set up, which we call planning. Planning is different. We tell it the environment. In the planning problem, we say, this is exactly the environment that you're working within. We tell it all the rules of the game, if you like. We tell it the details of the dynamics of the wind for the helicopter and how helicopters move. We tell it. We give it the differential equations describing wind and so forth. So the model of the environment is fully known. And instead of interacting with an environment, the agent performs internal computations with its model now. It's given this perfect model. It's given it computation time. It interacts with its model. Doesn't actually have to do anything in the real world. It just kind of thinks for a while, figures out what to do next. Maybe it's doing look-ahead planning. And as a result of those interactions, it improves its policy and comes up with a way to behave. But they're very different setups. In RL, the environment's unknown. In planning, the environment is known. Now, of course, one way to do reinforcement learning is to first learn how the environment works and then do planning. So they're linked. These two things are intimately linked together, but they're separate problem setups. So let's try and make this concrete again. So let's talk about the Atari problem again. So this, I already went through this slide earlier. But this was the reinforcement learning problem, right? We start, no one told us how this emulator works. We just put our machine in front of this thing, it's trying to figure it out through trial and error. We don't know the rules of the game, we just see the scores on the screen and get to control the joystick. That's the RL problem. What about the planning problem? What would that look like? So what if someone actually told us how the emulator works? What if we actually had access to a perfect emulator of these Atari games, and we were able to do look-ahead planning with that emulator? We could query the emulator. You could think of this as our perfect model now. We could say, if I was in this state here, in this game Sequest, and I move the joystick right, where will I end up next? Or if I'm in this situation here and I move the joystick left, where will I end up next? And this perfect model will tell us what happens, and that gives us the ability to do things like look-ahead search or tree search or planning. There's all these different planning methods where we can kind of think ahead, and we can say, well, if I went right and then went right again, then I'd get some oxygen, and then I'd shoot these different fish, and I'd end up with a reward of 100, without ever actually interacting with the real environment. So you can kind of build this whole search tree, figure things out, and that's the planning process. But it's a different problem setup. Right? We're told in advance the rules of the game. The environment's known. Yeah, question?
If there's more than only two actuators, like say multi-dimensional actuators, then this really quickly explains into multiple possibilities of that.
Right, okay. So the question is, what happens to the branching factor of this search space? So at the moment we're just talking about problem definitions. We'll have much more on how to plan effectively and efficiently and deal with large branching factors in later classes. So in practice we can do this. So I just want to cover, just before I take more questions, someone asked about exploration. So this is another problem within reinforcement learning. How do we balance exploration and exploitation? It's another key part of the identity of what it means to do reinforcement learning. So reinforcement learning we can think of as type of trial and error learning. You know, we don't know what the environment looks like. We have to figure it out through trial and error. We have to go find out which parts of the space are good and which parts of the space are bad. But the problem is that while we're doing that, we might actually be losing reward along the way. And so the goal is we want to actually figure out a good policy. We want to figure out the best part of this space. We want to figure out where the gold is in, you know, imagine you've got some pirate hunting for treasure. It wants to find the policy that has the most gold, but along the way, it wants to make sure that it's not giving up opportunities. Until it's found where the treasure chest is, it shouldn't be giving up the opportunities to exploit the things it has discovered. So the one way to say this is it basically gets to interact with experience. It's trying to find the best possible policy without losing too much reward along the way by exploring. So it has to balance exploration and exploitation. In other words, exploration means choosing to give up some reward that you know about in order to find out more about the environment. So, you know, maybe you think, given everything you've seen so far, you think that by going left you'll get the most reward, but you know that you haven't really explored right very much. And so maybe it's better to go right for a while, discover that there's a big treasure chest there, and so that in the future you might end up actually getting a lot more reward in the long run. So we've got this balance between exploration and exploitation. Exploration, find out more about the environment. Exploitation means exploit the information you've already found to maximize your reward. It's the exploration-exploitation trade-off. It comes up, you know, it's universal to reinforcement learning and kind of special to reinforcement learning. It doesn't come up elsewhere in machine learning. So let's just have some examples. So, you know, you all go to restaurants occasionally. So what happens if you're trying to pick the best restaurant? So what does it mean there? So exploitation means you kind of go to your favorite restaurant. Exploration would be trying a new restaurant. Now, how do you balance these? Like, if you never explore and keep going to your favorite restaurant, you kind of get stuck on something suboptimal. But if you explore all the time, you end up, you know, maybe eating food that you don't like because you're exploring a lot, and maybe you should have gone to your favorite restaurant a little bit more often. So you have to balance these things out so that you end up finding the best restaurant and eating delicious food along the way. The classic example of this, that's one of the big success stories of machine learning, is advertising online. So this is a big use case for a lot of this machinery, where you're trying to basically decide what advert to show on some banner on some website. So this would be like, you know, Google AdSense or something like this. And there's exploitation then would be to show the most successful advert, the one which people are clicking on the most. But sometimes you also need to explore and show some different adverts that haven't been displayed before to see if people will click on them. And maybe those adverts will turn out to be better, make more income. Or oil drilling, you might want to drill at the best known location, so you know that there's likely to be oil over here, so maybe you just keep drilling and drilling and drilling. But sometimes it might be a good idea to try some new location, drill down a bit, see if there's oil there. Or in game playing, you know, you might play the move you believe is best right now, or you might just try a completely different strategy, something quite experimental, see how your opponent responds. Maybe over the course of many games that will end up being more effective. Okay. So just to finish, okay. So final problem I'll just cover briefly, which is prediction and control. So this is another distinction within reinforcement learning between prediction, which basically means how well will I do if I follow my current policy. So someone tells me the policy, I'm given a policy, you know, if I walk straight forward, how much reward will I get? Now that's a different problem to someone saying, what's the optimal policy? Which direction should you walk to get the most reward? And typically what happens in reinforcement learning is we need to solve the prediction problem in order to solve the control problem. We need to be able to evaluate all of our policies to figure out the best one. And so if we go back to our grid world example, you can have a grid world like this. This again is something where you've got an agent that's moving around this grid world. It's basically gets -1 per time step, but if it goes to A, it gets a +10 reward and teleports to A prime. If it goes to B, it gets a +5 reward and teleports to B prime. We can ask, what's the value function for the uniform random policy? Like if we just move around this grid randomly, how much reward will we get? That's a prediction problem. we're just asking for this fixed policy of behaving randomly, how much reward will we get? This is the answer. You get, at best, if you're in this top state here, you get 8.8 units of reward in total going into the future, roughly. And we'll see how to solve these things in subsequent lectures. If we were doing control, we ask the question, what's the optimal behavior in this grid world? If I'm anywhere on this grid and I behave optimally, now what's the value function? And the value function is very different. So now if we look again at that best state, before we were getting 8.8, now if we behave optimally in this grid world, we get a very different answer. The optimal value, according to the best possible behavior, gives us like more than 24 units of reward, because we're going to follow this optimal strategy and loop round and round these links and get more and more reward. So now it means that if we're in state A, we can expect to get more reward in the future. So the optimization problem, the control problem, is very different to the prediction problem. Okay, so I just want to finish with the course outline, and so people understand what's coming next. So the course is roughly divided into two halves. I'm afraid because of last week it won't align with reading week, but we'll figure that out as it goes. But the first part is roughly covering the basics, covering really fundamental understanding of reinforcement learning. So introducing the problem we've just done, understanding Markov decision processes, how to plan, so solving the planning problem using dynamic programming, which is the elementary building blocks that underlie all of this, and then understanding model-free methods for both prediction and then control. In the second part of the course, we'll look at how to scale up, how to really apply, at the end of this part, you won't really be able to go off and solve interesting problems. You shouldn't have that expectation. But all of the ideas which we'll learn here do scale up, and in the second part of the course, we'll understand how they scale up and apply to more interesting problems by using value function approximation, policy gradient methods, integrating learning and planning using more sophisticated approaches, solving the exploration-exploitation problem. And so that's where things will become interesting. And then finally, in the last lecture, which is the one which we'll have to find a good time for that, I'll just give a case study, which is some of the success stories of reinforcement learning in games. And we'll see that RL has been used to achieve not just world champion performance in backgammon, but actually across all of the different classic games,